Imagine a sudden, absolutely blinding flash of light. In a fraction of a second, the air temperature right around you spikes to 35,000 degrees Fahrenheit. I mean, that is roughly 3.5 times hotter than the surface of the sun. Molten metal is suddenly shooting out at over 740 miles per hour, riding this massive thermoacoustic shockwave. Now, this isn't some crazy scene from a sci-fi movie. This is the very real reality of a high-voltage arc flash, a totally catastrophic event that can happen in the blink of an eye when working on electric vehicle systems. Welcome to This Explainer. Today, we're diving into a really fascinating intersection of modern convenience and, quite frankly, extreme hidden danger. You see, we live in an era where massive, fast-charging EV infrastructure can literally be dropped into a pop-up event overnight. It's incredibly convenient, right? But beneath the sleek casings of these mobile power stations and the vehicles they charge flows a force so immense that it requires military-level respect and specialized armor just to handle safely. So, we're going to bridge the gap between the booming trend of mobile EV charging and the rigorous safety standards required to survive the power it actually delivers. Here's our roadmap for today. First, we'll look at powering pop-up events. Second, the high-voltage threat. Third, the anatomy of an electric shock. Fourth, armor against the arc. And finally, emergency high-voltage rescue. All right, let's jump right into Section 1, powering pop-up events and on-demand EV charging. The landscape of electric vehicles is totally changing, and, so is how we charge them. We're not entirely tethered to permanent trenched-in charging stations anymore. Think about the sheer capability of these self-powered behemoths. If you're running a multi-day festival, a vehicle launch, or a ride-and-drive event, you need DC fast charging on demand. Take the ChargeRig's Flex, for example. It's a battery-powered mobile unit that delivers a staggering 120 kilowatts of power. It just rolls in, levels out, and starts charging vehicles within an hour. No permits, no digging trenches, and absolutely no emissions, which means it can even be used indoors. Then you have modular systems like the SparkCharge Roadie for really quick activations, or the Jenny IQ, which uses a diesel generator for continuous runtime over multi-day events. The convenience is just absolute. We're casually moving around equipment that handles mind-boggling amounts of electricity. But moving this much power around so effortlessly kind of masks a very serious physical reality. Which brings us to Section 2, the high-voltage threat and the fragile reality behind it all. So the absolutely crucial point here is this. It doesn't take much to kill a human being. According to the ASC Electrified Propulsion Vehicle Safety Standards, the lethal current limit across the human heart is a shockingly small 75 milliamps. That's 75 one-thousandths of an amp. We're talking about an almost microscopic amount of electrical flow, yet it is entirely lethal. Let's walk through the terrifying math straight from the ASC Safety Manual. Most of your body's electrical resistance actually comes from your dry skin. On average, let's just say the body's resistance under certain conditions is about 600 ohms. Now, a lot of EV systems operate at 400 volts or even higher. If you take that 400 volts and divide it by your 600 ohms of resistance, you get 0.66 amps. That is 660 milliamps of current coursing through the body. Put that into perspective. 660 milliamps is nearly 9 times that lethal limit of 75 milliamps we literally just talked about. And remember, once the skin burns, your body's resistance drops exponentially, meaning that current flow is only going to increase. Now for Section 3, Anatomy of an Electric Shock, where we'll look at the biological breakdown. It's wild to see the physiological breakdown at these different milliamp thresholds. At just 1 milliamp, you barely feel a slight tingling. At 5 milliamps, it's a disturbing but non-painful shock. But once you hit the 6 to 16 milliamp range, you enter what's terrifyingly known as the let-go threshold. This is a freezing current. Your muscles contract violently and just lock up. If you're holding a high-voltage cable, your hand will involuntarily clamp down on it. You literally lose the muscular control required to let go of the very thing that is shocking you. By the time you reach 17 to 99 milliamps, you're facing extreme pain and respiratory arrest. And from 100 up to 2,000 milliamps, the heart enters ventricular fibrillation. That's an uneven, uncoordinated pumping that just ceases blood flow altogether. At this stage, death is highly likely. And shock isn't even the only hazard. There's also fire. If the insulation between high-voltage conductors gets compromised, a plasma arc can form. This is that arc flash we mentioned at the very beginning of the explainer. It is a massive, explosive release of thermal energy. Again, we are talking about temperatures reaching 35,000 degrees Fahrenheit. The heat instantly vaporizes metal conductors, expelling this molten shrapnel at over 740 miles per hour. It creates blinding light, toxic smoke, and a shockwave that can literally throw a worker across a room. This is exactly why standard mechanic wear is completely useless around EV high-voltage systems. Moving on to Section 4, Armor Against the Arc, and how technicians are surviving the power. To survive a working environment where a single tiny mistake can result in a 35,000-degree explosion or a locking muscular shock, technicians have to adopt some truly meticulous physical armor. Think about the personal protective equipment, or PPE, mandated for Level 2 and Level 3 technicians. You don't just throw on any old gloves. You wear Class 0 electrical insulating rubber gloves that are specifically designed to stop 1,000 volts of alternating current. And because rubber can tear or puncture so easily, you actually have to wear approved leather overgloves right on top of them, just to protect the rubber itself. Technicians also wear ARC Class 2 face shields to shield their eyes and face from the blinding light and intense heat of an arc flash. They're decked out in flame-resistant garments and, note, flame-resistant doesn't mean flame-proof, but it's engineered to limit burns to a curable second-degree level by actively resisting ignition. They even stand on Class 0 rubber insulating matting to prevent themselves from being grounded in the first place. And this armor is subject to incredibly strict regulations, like those found under OSHA Table I-5. The testing intervals for rubber insulating equipment are no joke. Your life-saving rubber gloves must be electrically tested before they're ever even issued, and then vigorously retested every 6 months. On top of that, technicians are required to visually inspect them for pinholes or cracks and actually inflate them with air before every single use. If a glove's certification date has expired, even if it looks fresh out of the box, it absolutely cannot be used. It goes straight back to the testing lab. The margin for error here is exactly 0. Finally, let's look at Section 5, Emergency High Voltage Rescue, and the ultimate fail-safe protocols. Imagine seeing a technician actively being shocked. Human instinct just screams at you to grab them and pull them away, right? Well, if you do that, you'll likely die right next to them, because you'll instantly become part of that electrical circuit. The ASE standards dictate a rigid 3-step response instead. Step 1, call 911 immediately. Step 2, disconnect the source of the voltage. You turn off the ignition, kill the service disconnect, or pull the manual service disconnect if possible. But, if the source is the high-voltage battery itself, a disconnect might not even be an option. That leads us to Step 3, separate the person using a non-conducting object. And the absolute most vital non-conducting object in the shop is the insulated retrieval hook, commonly known as a hot stick. Let me be clear, this isn't just another shop tool, it is a critical lifeline. It's a closed-cell, non-conductive, foam-filled fiberglass pole designed specifically to hook onto a trapped, actively shocked worker and physically drag them away from the live circuit without transferring that lethal voltage back to the rescuer. It's a pretty stark reminder of the massive physical stakes involved in this technology. This brings us to a final thought for you to consider today. The whole EV ecosystem is evolving brilliantly. The ability to drop a 120-kilowatt mobile charger right into a weekend festival is an absolute marvel of modern engineering, not to mention peak convenience. But as this massive power becomes seamlessly integrated into our everyday spaces, we have to ask ourselves, as mobile charging brings massive power anywhere we want, are we truly ready to respect the lethal forces it carries? The power to drive the future is incredible for sure, but as we've seen today, the responsibility it demands from those who handle it is absolute. Thanks for joining me for this explainer, and keep learning.